ladies and gentlemen, it's Mrs. Hoekstra here. I'm working on Module 1, Lesson 7 today. It's about unit rate and the constant of proportionality. Make sure you're on page 23 of our text. All right, and let's start by writing in our EQ. Our essential question of the day, right? What is the constant of proportionality? What is the constant of proportionality? One other question to this, though. How is it identified? How is it identified in an equation? Okay, what is the constant of proportionality and how is it identified in an equation? There we go. So by the end of this lesson, you should be able to figure that out. All right, example 1, national forest deer population in danger, right? So we've got these wildlife conservationists, and they're concerned the deer population might not be constant across the national forest. Scientists found that there were 144 deer in a 16 square mile area of the forest. Okay, I'm going to circle that, kind of important. I'm going to do it in one color, so maybe if you're working in a highlighter, you could highlight this data right here. Well, it helps if I have the right tool on. If I highlight this data right here, right? 144 deer in 16 square mile of the forest. In another part of the forest, right, a different conservationist, they counted 117 deer in 13 square miles. And a third conservationist, change your color, counted 216 in a 24 square mile, right? So if we take a look at the data, let's keep track of what they did. I like to have it organized in a table because it just makes it easier for me. Okay, so what I'm going to do is I'm going to take a look at that first one. The first one was 16 square miles. There was 144 deer, right? Notice I kept that color the same. So maybe if you wrote in highlighter, you could highlight that in that same color that you used in your story. 117 in 13 square miles. And we have 24 square miles. There was 216. Well, the question is this, constant? Is it proportional? Does it stay consistent across all of those? And those numbers seem very strange to me. So in order for me to figure this out, I'm going to find the unit rate. All right, let's find the unit rate. In order for me to find the unit rate, I am going to take the number of deer, the Y value, and I'm going to divide it by the square miles, right, the X value. I want to know how many deer are in a square mile, right? Deer per square mile, that's how you would say it, deer per square mile. So I'm going to take the 144 and divide it by 16. And when I do that, I get 9. 9 deer per 1 square mile. All right? If I take the 117 and divide by the 13, I get 9 deer per square mile. Well, at least those two are consistent. Is it constant when I take the 216 and divide by 24? Yep, I get 9 deer per square mile. So the population density of deer per square mile is the magic number 9, right? There are 9 deer per square mile. What is the constant of proportionality? Well, the definition of the constant of proportionality, so here I am answering the EQ right now. It is the fixed. What in the world does that mean? Fixed just means constant, right? It's constant, stays the same. Oop. Let's just start that over. Constant, it stays the same, right? So fixed just means constant or always stays the same. It's the fixed unit rate. So in this case, it was 9, right? Well, what does that 9 mean? So let's give that definition again. It means in our problem here, there are 9 deer per 1 square mile, right? So if I did a mile by mile square, put a fence around it, I should find 9 deer in that big square. All right, so we're supposed to use the unit rate of deer per square mile, or y over x, to determine how many deer there would be if it's 207 square miles, right? So this is a huge park. Think of it like maybe Yellowstone, right? And so how many deer would we have? So what we're going to do is we're going to take and figure out the number of deer is equal to 9 times the number of square miles. All right, there's my formula in words. So the number of deer is equal to 9 times, now in this problem, it's 207. So how many deer would I have? 9 times 207. I should expect 1,863 deer in that big park. All right. Well, let's suppose we're at a different park. The conservationists went somewhere else, and they want to know, in the next problem, if I counted 486 deer, well, how big is the park, right? You're like, I don't know how big this park is. Okay, so what we'll do is we're going to use the formula slightly differently. We're going to take our square miles. To find that, we're going to take the number of deer and divide by the 9. Divide by that constant rate. So our square miles, how big is this park? Well, we have 486 deer, right? And we're going to divide that by the 9. How big is this park? It's 54 square miles. Or you could write miles squared, or you can write SQ for square miles, right? Either one would be fine. You can write it either way. I will accept them both. So ultimately, the question is, do the conservationists need to be concerned? Do they need to be worried? If you go way back up at the top, is it constant across the whole thing? Yeah, right? There's always 9 deer. So the conservationists really don't need to worry about if the deer population is constant or not. Well, on the next page, we've got a couple vocab words. All right, so let's write those in. Our first vocabulary is constant. Constant is just a unique number that never changes, okay? A unique number that never changes, right? The number 3 always is the number 3. We know exactly what 3 things are, right? It's not like 3 is, you know, this and then 3 the next day is something different. It stays the same. Variable, on the other hand, right? Variable. Notice the word vary, right? The root of it is vary. So a variable is a letter or symbol, right? We could put a smiley face emoji in there. It would still work. It's a letter or symbol that represents, it's a letter or symbol that represents a number that's unknown. So now that it's unknown, it does vary. It can change, okay? It's a letter or symbol that represents a number that's unknown. In one time, it could be the number 3. Another time, it could be the -7. We don't know. It's going to vary depending on what's going on. All right, unit rate. This is a word we've already used, but let's review it again. A unit rate is a proportion. Unit rate is a proportion with a denominator of 1. Okay, it's a proportion with a denominator of 1. Examples, right, would be miles per hour, right? 1 hour. How many miles did you go in 1 hour if you're running? And then there's constant of proportionality. This is our key for today, right? This is the big one that we need to know. The constant of proportionality is a value. No, let's pick green. It's a value that represents the multiplicative, ooh, big word, the multiplicative, big word, multiplicative relationship between two quantities. Between two quantities. All right. Now, when we work with the constant of proportionality, we use a variable to represent that, and we use the variable k. All right. We use the variable k to represent the constant of proportionality. So I purposely misspell constant in constant of proportionality. K, I write it as the constant with a K. Constant of proportionality. All right, and then that helps me remember. Oh yeah, K, constant of proportionality. Whenever you see the constant of proportionality, we usually write it in some form of an equation, and generally the equation is y is equal to k, whatever that constant is, times x. Okay, there's our equation for constant of proportionality. That's the one we really need to know today. Let's try example 2. Brandon came home from school and informed his mother that he had volunteered to make cookies for his entire grade level. He needs 3 cookies for each of the 96 seventh graders. Unfortunately, he needs them the next day. He didn't tell Mom until the night before they were due. Brandon and his mother determined that they can fit 36 cookies on 2 cookie sheets. All right, create a table that shows the number of sheets needed for the number of cookies baked. So let's just go back to the original, right? 36 cookies on 2 sheets. 2 sheets, 36 cookies, right? Now we can just do some variations of those. So let's do what? 4 cookies, or excuse me, 4 cookie sheets. They can bake 72 cookies. Let's suppose they use 10 cookie sheets. They would make 180, right? Let's suppose they did 16 cookie sheets of cookies, 288 cookies. And let's just go really crazy. They used 20 cookie sheets. They would have 360. That ratio, that proportion has to stay the same. So is the number of cookies per cookie sheet, right? Is that proportional? That's that first question. Yes, it is. This is proportional. Right? This is proportional because, remember I use my crazy abbreviation for because, they get, what, 36 cookies, whoop, 36 cookies for every 2 sheets. Those could get reduced, I think. They're both even, right? So I think I'm going to turn that into 18 cookies on 1 cookie sheet, right? So what's the unit rate? Well, we just calculated it, didn't we? The unit rate, we just found it to be 18 cookies for 1 sheet. That must be a big cookie sheet because I don't think I could fit that on mine. Well, that unit rate becomes the constant of proportionality. Aha. So in other words, unit rate and constant of proportionality, they're the same thing. Okay? They are the same thing. It's kind of like if you have a name that your parents gave you, but then you have a nickname that your friends call you, right? You're the same person. Same thing here. Unit rate and constant of proportionality are the same thing. So my constant of proportionality, my unit rate, is 18 over 1. But 18 divided by 1, I could just write it as 18. Either one of those are going to be acceptable answers. All right? Let's go to the next page here. Keep going with this problem. Oh, that's not the right page. There we go. And it says, explain the meaning of the constant of proportionality. Right? What does this mean? What does that 18 over 1, right? What does 18 over 1 mean? It means they can place 18 cookies on one cookie sheet. That's what that means. Okay, ultimately, how long is this going to take Brandon and his mom to make all these cookies? Okay, so if you go back and look across the page there, it says that he is going to make 3 cookies for every student. There's 96 students in his grade, and he's going to make 3 cookies for each one. All right, so 3 times 96, you grab your handy dandy calculator, you find out they need to have 288 cookies made. Okay, so they need to make 288 cookies, right? If you look across the page, I think we had figured it out, that 288 cookies divided by the 18 on a sheet, right? I need 16 sheets of cookies, right? That's on that table across the page there. Well, it tells us that it takes what? 2 hours. Look at this. It takes 2 hours to do 8 sheets of cookies, right? So if I take the 8 sheets of cookies, divide it by the 2 hours, in other words, they can do 4 cookie sheets per hour, right? So if I take that, I need 16, right? So in other words, if I multiply this by 4, or I could have multiplied the first one by 2, right? That would give me my 16 sheets. And 1 times 4 is 4 hours. So it's going to take them 4 hours to bake all these cookies. They started at what time? They started at 4 o'clock. So if they start at 4 p.m., and you add another 4 hours to that, what time do they finally get done? They get done at 8 p.m. I think Brandon's mom deserves an award for that. Okay, so don't you kids do that to your mom or dad, because, you know, they've worked hard all day and they're tired too. All right, let's take a look at example 3. Example 3, Suzette and Margot want to prepare crepes. I know most of you say it's crepes, but it is crepes for all the students in their French class. A recipe makes 20 crepes. Let's underline that. We're going to make 20 of them. Circle it, I should say. And you need flour, milk, and it calls for 2 eggs. Okay, the girls already know that they have plenty of flour and milk, right? That's already set. They need to make 50 crepes. I'm going to underline or circle that one, maybe with a different color. But they don't know if they have a right number of eggs, right? They need to figure out how many eggs will they need. Well, let's figure this out. Considering the amount of eggs necessary to make the crepes, what is the constant of proportionality? Now remember, constant of proportionality is also the same as unit rate. So I just need to figure out what the unit rate is. So if I take 20 crepes and I divide by the 2 eggs needed for those 20, I can really make 20 crepes or crepes, however you want to say it, over the 1 egg, right? I only have 1 egg in the house. How many could I make? I could only make 10. So there is my constant of proportionality. I could call it 10. I'm going to label that the letter K because that's my constant of proportionality. So what does it mean? They can make 10 crepes with 1 egg, right? That's what that constant of proportionality means. How many eggs then do they need to make 50, right? They're going to go to French class tomorrow. They're going to make 50 of these. So to make 50 crepes, I'm going to divide by the 10, or our constant of proportionality, and I need to make sure I have 5 eggs. All right, that is it for lesson 7. I hope you guys have a great evening. I'll talk to you guys later.